Welcome back. If you've been following along with our operating systems playlist, you know we've covered what an OS does. But now, we're diving into one of its most critical jobs, playing defense. How does your OS protect itself, and more importantly, all of your data, from attacks? Today, we're going to build that digital fortress, piece by piece.
But first, let's get a big question out of the way. Can we ever build a perfectly secure system? 100% unhackable? Well, theoretically, maybe, using some really complex math to formally verify every line of code. But in the real world, the systems we use are just way too complex. So the short answer is no. This isn't about eliminating risk completely. It's all about managing it. So here's our game plan for today. First, we're going to survey the battlefield, understand the threats we're actually up against. Then, we'll start building our fortress's defenses, layer by layer, looking at how an OS controls who gets in and what they can do. And finally, we'll see what happens when those walls get breached. All right, first things first, why all the fuss about security? Well, before we can even think about building defenses, we need to know what we're protecting, and maybe more importantly, who we're protecting it from. It's all about setting our goals and knowing the threats. At its very core, OS security really boils down to protecting three key things. You might have heard of it as the CIA triad. First up is C, confidentiality, basically keeping secret secret. The threat there is data disclosure. Then we have I, integrity, which is all about making sure your data is accurate and hasn't been tampered with. And finally, A, availability. This just means the system is actually up and running when you need it, which is threatened by things like denial of service attacks. So who are these attackers anyway? Well, it's a pretty mixed bag. You've got your criminals and corporations who are purely motivated by money. You've got government organizations playing for a strategic advantage. And sometimes you've got hackers who are just in it for the fun or the challenge of it all. Okay, let's start building our fortress. Our very first line of defense is all about controlling access. Once a user is inside the system, how does the operating system decide what they can and can't touch? This is all about permissions for files, devices, you name it. The fundamental idea here is something called a protection domain. The easiest way to think about it is like a rule book for any process or user. It's just a set of pairs, where each pair links an object, like a specific file, to a set of rights, like read or write. Every single thing running on your computer operates within one of these domains. Now this is where it gets really interesting. There are two main ways an OS can enforce these rules. On one hand, you have an access control list, or ACL. With an ACL, the permissions are attached to the file itself. Think of it like a guest list on the door of a club. On the other hand, you have capabilities. Here, the permissions are given directly to the process. That's like giving someone an all-access backstage pass. They each have their pros and cons when it comes to flexibility and speed. And you actually see this every single day. If you've ever used Linux or macOS or any other Unix-based system, you know that every user has a user ID or UID and belongs to groups with group IDs. The OS uses these IDs to check permissions on files. It's a simple but super effective type of access control list. Okay, so the gates are up and the guards are in place. But how does the OS know who's actually knocking at the gate? That brings us to our next critical layer, authentication. The secret handshake that proves you are who you say you are. Modern authentication is really built on these three pillars. It's all about verifying your identity using 1, something you know, like a password; 2, something you have, like your phone or a key fob; or 3, something you are, like your fingerprint or your face. And as you probably know, the most secure systems use a mix of at least 2 of these. And man, have these methods evolved over the years. We started with simple, reusable passwords, which, let's be honest, are just terrible for security. Then we got a bit smarter with things like one-time codes sent to our phones. Today, biometrics like Face ID are pretty standard. But the future is all about getting rid of passwords entirely. And that future is already here with a standard called WebAuthn, which you probably know as passkeys. This is a real game changer. It uses some powerful cryptography so that your device can prove your identity without ever sending a secret password over the internet. This is a massive leap forward in stopping phishing attacks cold. So, we've let our user in, and we've set their permissions. Our fortress seems pretty solid, right? Well, what happens if there's a flaw in the code of the programs themselves? Now we're going to look at how attackers exploit software vulnerabilities to sneak past all of our defenses. Let's start with an absolute classic, the buffer overflow. So, in a normal, healthy program, memory is organized very neatly. The program has a little area of memory called a buffer to hold input, and somewhere else, it stores the address of where it needs to go back to when it's done with the task.
And boom, here's the attack. An attacker sends a specially crafted, oversized chunk of data. This input is too big for the buffer, so it overflows and spills into the memory next to it, overriding that legitimate return address with a new, malicious one. Now, when the program tries to return, it doesn't go back to where it's supposed to. Instead, it jumps right into the attacker's code.
This, as you can imagine, kicked off an amazing cat-and-mouse game. First, defenders came up with something called the no-execute bit, which marks certain parts of memory as data only, so you can't run code from there. But attackers are clever, so they came up with return-to-libc attacks, where instead of running their own code, they just jump to existing functions in the system's core libraries. So then defenders fought back with address space layout randomization, or ASLR, which shuffles the location of those libraries in memory every time a program runs, making them a much harder target to hit.
Of course, buffer overflows aren't the only trick up an attacker's sleeve. You've also got things like format string attacks, where they can manipulate how text is printed to read or even write to memory. And then there's command injection, where an attacker tricks a program into running dangerous system commands. Yeah, that one is just as bad as it sounds. All right, we have covered a ton of ground. We've gone from the high-level goals of security all the way down to the nitty-gritty of how specific exploits work. So let's just take a step back and quickly recap the key defensive layers of our digital fortress.
So what's the big takeaway here? The most important thing to remember is that a secure fortress isn't just one big wall. Real security is a strategy called defense in depth. It starts with knowing what you're trying to protect, then you build layers. The gates and guards of access control, the secret handshakes of authentication, and you're constantly patching and reinforcing the walls themselves against software exploits. Hey, if this explainer helped you wrap your head around the fundamentals of OS security, do us a huge favor and hit that like button. And make sure to follow for more deep dives into how our digital world really ticks. Thanks so much for watching.